So application temperature, this is the typical pyramid of fluoropolymers and plastics. The funny thing is that we also added the bottom. So not only above temperatures, but also cryogenic temperatures. So there is a handful of plastics which can go above 260. 260 is the maximum continuous temperatures of fluoropolymer, of many fluoropolymers and PEEK. Then you can see PCTFE is down to 150. What is interesting is the bottom line that we're going to focus in today as well, which is the cryogenic temperatures. Okay, to begin with, what you think of as a cryogenic. As a salesperson, as an engineer, you may come across many situations when someone says, oh, this is a cryogenic application, minus 40, minus 50, minus 60. Now we hear about the vaccine in minus 80. Well, indeed, it is a cryogenic, but when it comes to a fluoropolymer, I would not define a minus 50, minus 90, minus 100 as a typical cryogenic application. Generally speaking, for sure, the properties of a fluoropolymer will change also minus 50. We're going to see some slides, but a standard PTFE in many applications will be likely to work absolutely fine. So minus 50 for a fluoropolymers is not a very challenging temperature. It is for many other plastics, it is for rubber, is not for a fluoropolymer, is not for PEEK either. A typical cryogenic application is minus 196 or liquid nitrogen, up to minus 250. There is no, I have no knowledge of many technical information below that temperature because it gets very difficult also to do testing and reporting. As you see, we have put down all the fluoropolymers to minus 250. In fact, you may be able to use any of those. It's not that at minus 200, 250, you cannot use a standard PTFE. But all these fluoropolymers, they do behave in a different way, and we're going to see that. So the best material, to the best of our knowledge, for this cryogenic temperature is PCTFE. If I have to name one plastics which has changed the industry in the past decades, that is definitely PEEK. PEEK has been a great breakthrough. It has really changed what we can do. Maybe in our daily life we don't realize that, but in the engineering world it does. For example, one quick example, the pressure that a valve can take. The pressure that a valve can take has been changed thanks to the sealing, the inserts that can be done in PEEK compared to other fluoropolymers. I thank Vitrex for this slide. Just out of curiosity, you may see the original US patent granted in 1982 to IECI for the PEEK. So this is the birth certificate of PEEK. As I said, it dates back to 1982, submitted by IECI, the chemical industry UK, and then the Vitrex has been a spin-off of this company. This is as a piece of curiosity. All right, let's go ahead. So why PEEK is what it is? Well, many properties. It is a pure material. It has an exceptional hydrolysis resistance. We will see an interesting graph on how and to what extent PEEK can be used in water and steam, for example. It is very strong, high strength compared to the weight. one of the main characteristics of PEEK is its mechanical strength. Okay, and it is very light and yet very strong. This goes together with the wear resistance. Chemical resistance, well, okay, we know that PTFE is not a king, it's the emperor of chemical resistance, so there is no plastics like PTFE. All fluoropolymers are at the very high end, but just a step beneath is PEEK. Again, among all plastics, PEEK has a terrific chemical resistance. Temperature performance, we already saw, goes up to 250, but also for cryogenic application, we're going to have a quick look later on. Don't get scared about a few graphs. So this is a function of strain and stress. So how much strength do I need to apply to break PTFE if I tear it up in relation to the temperature? And so the first line is very steep. It means I need quite the strength to break it up, but of course there is a low elongation because it is a room temperature. Going on in temperature, material becomes more elastic. So I think this is what we can say that is what we expect a material to behave. I think this is quite interesting. So is the retained tensile strength of unfilled PEEK, Flutek K300, versus conditioning time at high temperature in water. Let's start from the column in the middle, water. Okay, you can leave PEEK in water at 75 degrees for 1,400 hours. And what happened when you take it out? You find out that the tensile strength of PEEK is the same. And this is quite a performance, I would say, and it is quite an information. So it doesn't age. It has been not affected. If you put PEEK, let's go to the left, to seawater is chemically aggressive. What happened? The performance is quite challenging anyway, because we have 100 degrees seawater for 672 hours. You have a slight decrease in tensile strength, but yet look at the performance. After all this time, it retains almost all its tensile strength. To the left, even more interesting, 2000 hour PEEK sample in steam at 200 degrees. You eke it out, and what you find that the material is even stronger. Tensile strength is even higher. So this is an information. You can definitely use PEEK in steam if you're looking for mechanical properties. Why is that? Well, the reason being, in this case, PEEK is undergoing what we could define kind of a curing, what we could define as a part of annealing. So it's undergoing a second crystallization process. It's like if it's being annealed to some extent. This is why when you take it out, it is actually stronger than what it was at the beginning. Like many other plastics, PEEK can be filled. We have a few examples here. Not so many fillers available for PEEK as for other plastics, for sure not as many as for PTFE. One of the most common is what we call the K303, which is 10% carbon fiber, 10% graphite, and 10% PTFE. It's a typical tribological application. So a carbon fiber to give more wear resistance, graphite and PTFE to help to lower friction. Typical material for sealing application. What we call PEEK K301 is a 30% carbon fiber. This is the very high end of PEEK when it comes to stiffness and strength. Well, not only in PEEK, I I would take that among all plastics, this is one of the strongest plastics that you can have. The weak point is very fragile, very brittle, and very low elongation. Flutec K304 peak to at 20% PTFE, a very niche material. We have developed and we sell with success for the oil and gas industry. Why is that? If you add a 20% PTFE to the peak and you use it for a seat or for an insert, what we find out is that the pressure the peak can take is anyway quite high. So yes, it may decrease a class. This is to be seen according to engineering, sizes, diameter, and so on. But it remains a strong material, and yet with a 20% PTFE, it does lower the friction. What it does mean, you need less torque to activate the valve, and valve producers do really like that, to lower the torque. Cryogenic peak, well, is a newly developed material. There are a couple of grades developed by Vitrex for extreme low application. Is a material which contains PCTFE when it goes to minus 200. It can take bigger pressure, is still a newly developed material, but we have been processing it with success. If you have special requests, please ask. Now, a note which is true for many plastics, not everything which is on paper is really available all the time. If you look at the more common plastics, let's take a nylon, for example, there is such a wide array of suppliers, and you can most likely find what you need, or at least there is such a big market, and big market means big supply. Well, the higher you go to the chain, the less it is. And when you come to high performance material, well, apart from PTFE, which is a complete different market, a complete different set of processing, and as a fluorseals, I can say we cover a very well, almost all the range of what is available. Well, for peak and other high performance materials, be careful. Not everything is available in all shapes, size, quantity that you like. Let's make an example. Oh, I see the peak 30% CA. Good. I really need a very strong material for my application. Good. That sounds perfect. I need a sheet which is 100 millimeter thick. Sorry, you're not gonna get that. Or if you get, it's gonna take time, it's gonna take a lot of money, it's gonna take a minimum quantity. So this is all to say, going up in the chain, you really need to speak to your supplier, to your partner, to your processor, and be careful about what you need. Not everything is available. Quick look, technical properties of peak compared to field. This graph is to show how much strength in percentage you get by adding glass or carbon fiber, okay? And the higher the temperature, the more the filler helps, okay? We have glass, was no mention before. Glass is another standard filler used in peak. So high mechanical strength, a high temperature, you have to go for a filler. For PTFE is pretty much the same thing. Spin cast technology. Okay, rotomolding, also called, is been around for a while as a technology, but mostly used for common plastics and large components, not the high end of a technical spectrum, I would say. Well, for PEEK is different. PEEK is different because it's more challenging material and you need very high temperature. So do a spin cast technology on PEEK is not as doing for common plastics. In fact, there is a handful of companies that can do spin cast of PEEK. And yet it is a very nice technology if you need a billet in PEEK. Why is that? Some advantages. We compare it to compression molding because up to a certain diameter, the most common that you're gonna find in billets are compression molded. So it's right to compare rotomolding with compression molding. Well, the first technical aspect that comes along for sure is elongation. Okay. In data sheet, you may find many different numbers. And in fact, this is just because it really depends. Depends on the on the different compression molding, on the powder, on the sizes, on how you test it. You really have a wide range of numbers coming along. Nevertheless, one thing for sure, spin cast molding is much more flexible. In our data sheet, we put down 14. In reality, we are a bit conservative. We regularly test. We are much higher than that. Can be 20%, but we've done also 30, 40. I mean, we cannot promise that. We can promise it's going to be a flexible material for what is big, for sure. Without going into detail too much into all of it, machinability. Spin cast peak is much better to machine. Just the way you machine it, the scrap, you can see it's not powder-like. It's very flexible. It's much easier. But there is a very important point when you machine a spin cast peak. And its ability, to some extent, to keep the tolerances and to keep the diameters that you want. We know the tension build up inside plastics for semi-finish, typical problem. But this problem is really at a high level when you try to machine a compression molded peak billet. And this is nobody's fault. Well, the fault is the technology itself. But there is a reason for it. You put the powder into the mold, you go up to the sintering pressure, whatever it is, above 300 degrees. And then this material from 300 and whatever, it goes down to room temperature. And the plastics peak will like to say, well, I really would like to move here. I'm going from 300 to 20 and I like to move, but I can't. I'm inside the mold. What happens? It does build up a lot of tension. And this tension, they come up when you machine it. You can do an extra annealing. We do extra annealing. This is going to help up to a point. And the problem is that no matter what you think of, you never really know what's going to happen when you machine it. Because if you could say, oh, well, it's going to shrink 0.5%, it's going to shrink 1%, it's going to shrink 1 millimeters, you never know. Okay, my experience. It's very hard to tell. Too many things come along and you don't know. Depends on how the bill has been processed, depend on the powder, depend on the wall thickness, depend on diameters. You just have to live with it. And compression molding, this is a problem. Spin cast billets, they are free to cool without a mold. What does it mean? They release the tension. What does it mean? When you go and machine it, they are much more likely to keep the tolerance that you're after. Also, look at the left, no voids, starting from the bottom. We sell, well, I don't really know in numbers, but hundreds, if not thousands of billets a year. Honestly, I don't recall one single reject because of voids. Spin cast billet, if they are done properly, they don't get voids inside, okay? More likely in a compression molding where you need the operation of putting the powder in and microbubbles may stay. Commercially speaking as well, rotomolding is a flexible technology. You can change a wall thickness without the need of a new mold. Up to a point, because that's maybe the drawback of spin cast. The wall thickness should not be too thick. What do we mean too thick? Depends. Anyway, above 25 millimeter is almost impossible, at least for what we can do. This is it for PEEK. I hope it was interesting. Quickly, let's move to PCTFE. Let's go back to our family, to fluoropolymer. Is a semi-crystalline melt processable fluoropolymers, and this is the material of choice for liquid gases and situation of extreme cold. Properties of Flutex C100, sorry, my mistake, is C1000, it's not C1000, it's C100. High mechanical resistance, yes, we're gonna see a very interesting graph later. I'm gonna speak that later. Not flammable, this is a key point. This is a key point. Not everybody knows the LOI index, liquid oxygen index. But this is a key point of the use of PCTFE. You need above 95% of concentration of oxygen to make PCTFE flammable, meaning it's almost impossible to get it flammable. Meaning when it's used in liquid gases, this is something that the people really want. PCTFE does not spark up, okay? Chemical resistance, as many fluoropolymers, okay? We know it doesn't go up as to PTFE, so you may check some situation, but generally speaking, very good. Resistant to ultraviolet, water, moisture, and permeability. PCTFE is a very good barrier. We're gonna look later at PFA, and I'm not sure you wanna use PCTFE because it's a good barrier unless you're looking at cryogenic application. I think this graph is very interesting, okay? Don't be scared. It took some time for me to understand it as well, but once you get it, it's very, very interesting. So let's take a 30-degree, okay? So go to the far right. At 30-degree, a PTFE is 0.8 bigger than what it is at zero temperature, okay? Well, from 0.8 increase, going down to 200, minus 200, it shrinks to 1.2%. What it means you have a change from 30 to minus 200 of 2%. 2%, just think of your seal, which is 100 millimeter. What happened at minus 200? 98. I don't see many drawings which allow 2 millimeter change on 100 millimeter, honestly. I don't see drawing which allow a 2%, but that's what happens. And you know, if you're designing something which needs to go at minus 200 and you're using a PTFE, well, this is physics, chemistry, there is no discussion. You have a 2% shrinkage. You have to live with it. PCTFE, well, if you look at the graph, without doing all the math, I tell you, is 1%, more or less. 1% shrinkage. You may think is a lot. Well, it's 100% less. Is instead of 2 millimeter, if you have to engineer something, is 1 millimeter. It's a huge change. So this is one of the reasons why you may want to use PCTFE compared to PTFE, a very low cryogenic application. It does has a much lower shrinkage. Not only that, comparable tensile strength of Flutex P1500, which is our premium PTFE, compared to C100, the PCTFE. The lower the temperature, we have data, in this case, only up to minus 50, but look at minus 50. PCTFE is more than double as strong when it comes to tensile strength in megapascal to premium PTFE. Okay, and this is again quite an information. Going up to the temperature, and this goes away. That's what I said. If you need a PCTFE, consider what it costs. It has a reason at lower temperature. PCTFE has been added to the portfolio of fluorseals in the past years. We really thought it was important for our customer. It is a niche material, numbers are what it is, but it is a very high-end application. As you can imagine, anything which has to go at minus 200 must be top end. We thought it was important to add it, and we did. We now have a very, very wide range. It goes from extruded material to 4 or 5 millimeter up to 40, 45, compression multi-rods up to 100, which is very, very challenging to do, and we do. Sheets as well, in different sizes, 300, 300, up to 500 and 500, up to 50 millimeters. So again, we did a sheet which is 500, 500 for 50 millimeter sheet. So thick, quite a sheet, I would say. And we also keep a wide range of stock. Honestly, we can say we have a very, for what PCTFE market is, I can claim that we keep a very large stock for our customer. Don't get scared. Don't get scared. I'm scared myself. I'm not a chemical guy, so I'm not gonna be able to explain you this. But believe me, this slide is very interesting, and it is our introduction to PFA. Let's look at the bottom. Chain length compared to degree of modification. Chain length is the chain of a polymer, okay? So the longer the chain, which is the case of PTFE, the less degree of modification. So the less you have the standard processing techniques available. In fact, up to some years ago, all the company producing PTFE were doing kind only of PTFE. And so the other way around, whoever was doing the other plastic was not really doing PTFE. Why is that? Because you need a different technology, because the chain of the material is different. And this difference in chain length means you need to change your technology, okay? And this is interesting. On one side, PTFE, in the middle, kind of in between, modified PTFE, but yet it is still on the side of PTFE. You still need the technology that you need for PTFE. And then on the right, PFA. Where is the difference? The difference is this PPV, a modifier. I'm not going to tell you what it is chemically, not able to explain, but it's interesting the number, a 3% modifier in the chain of PTFE, and you get a PFA. And what you get? You get a thermoplastic processing technologies available. You can do transfer molding. You can do standard screw extrusion, okay? Just because you have 3% modification in the chain, something that PTFE doesn't let you do. PFA properties. PFA shares all the major properties of fluoropolymers, okay? Chemical resistance, low friction, low surface energy, weathering, so on and so forth. We're gonna focus on one though, one of the characteristics of PFA, which I think could be interesting. What is that? Is the permeability. We have three graphs showing the same thing. How PFA outperforms PVDF and PTFE in permeability. This is toluene, 80 degrees. Nitric acid, 80 degrees. You definitely don't want to use PVDF. You may use PTFE, and yet PFA is slightly better than PTFE. And also in water at 80 degrees. What that tells those graphs, they tell us that PFA is a very good barrier material. This is why it's used, for example, in semicon, where you have aggressive chemicals and very, very sophisticated devices that need to be protected. So PFA is, in this case, the material of choice. Also in this case, fluorseals added what we call Flutic F100, our PFA brand. Again, we have a very wide range of stock shapes available. Extrusion, in this case, up to 80 millimeter, but also compression molded tubes and billets, up to 1,000. Sheets, again, in several sizes, from 300 to 500, 500. Here as well, we did a sheet which is 50 millimeter thick, which is quite a challenge. Came out very well, very good. Skive tapes, niche market, because PFA can be extruded, as we said, but there are cases where you may want a skive tape in PFA, and we can do. And again, we keep a large stock compared to what PTFE as a semi-finish is being used. Finally, last but not least, a new product. We go back to our PTFE, and this is a Flutec P OG, which means optical grade. Is a PTFE specifically designed for lighting industry, for technical application in the light industry. Very quickly, let's look at the graph on the right. Okay. The column means that you can have PTFE optical grade ranging from white to black. Of course, in relation to the color, you have a different degree of reflectance. The standard pure 100%, oh, this is pure 100% PTFE, okay? There's nothing in it, okay? Just pure 100% PTFE. It's just a different grade. What you have, a reflectance of 98%, which at the same wavelength. And this is a very important information for anyone who is in the lighting industry. On the other side, if it's completely back, the degree of reflectance is very low, okay, 5%, something like that, which is lower than what you would have with a black standard PTFE, okay? So coming to the reaction of lights, this is material which can be very reflective or absolutely not reflective. Where it is used, oh, sorry, my fault. Why is that? Why does the optical grade has these characteristics? Is due to the surface. And we see on the right what happens to the light coming in. In fact, another way to describe optical grade is porous PTFE. So the surface is different, okay? The difference is in the surface. If you have any customer that operates in the industry that you see on your left, then they may use optical grade PTFE. So please ask, and fluorseals is here to support you. We're very flexible, whether it's a rod, a sheet, a tape, or a machine part. We are in the position to offer several components. Thank you very much. I hope it was of interest. That's about it for me. Okay, I don't know if there is any question, if I can help. No. Sorry, guys, I don't see the chat, so hold on a second. The maximum length that we do on extrusion goes from 3 meters to 1 meter, depending on diameters. Okay. That's it. Thank you very much for coming in. I hope you like it. Bye-bye.